In this lesson, we'll discuss the amplifier constraints. So essentially, we introduced the two-port network, and then we talked about linearizing the two-port network using Taylor series. And once you neglect the higher-order terms and then take only the first-order term, you will get a linearized form of a two-port network or a linear two-port network, which you have done it in your basic networks course or basic circuits course, and you know how to deal with linear two-port networks. Okay, and we came up with a circuit. We came up with a circuit something like this. This is y11 and this is y12 v2. Okay, and this is y21 v1 and this is y22. Okay, this is a circuit. This circuit was the result of the linear two-port expression that we got out of Taylor series approximation, right? And let me also put down the expression. The expression was something like this. So let me just mark the parameters, independent and dependent variables. So this is port 2, this is port 1. Okay, and this I said was common. Okay, while you can, I have assumed that the common terminal is 0, okay, or grounded, and that is why in the expression also, when I wrote the expression, it was something like this. I1 is equal to y11 v1 plus y12 v2. Okay, and I2 is equal to y21 v1 plus y22 v2. Okay, but this is under an assumption that this common terminal is grounded. Okay, but this need not be grounded all the time. That was just an assumption for simplistic expressions. But then you can call it terminal 3 instead of common, and you can say it is not grounded. But then you can write all the same expressions and all these things with respect to terminal 3. For example, this potential will be V13 and this also terminal 3 because they are shorted, so this potential will be V23. Okay, and here also V23 and V13. Nothing else will change. So everywhere I should write it with reference to potential terminal 3. That's it. Okay, if you assume terminal 3 is common, or terminal 3 is anyway common, if you assume it to be grounded, then this 3 will not come everywhere, it will be just 0. Okay, so now given this is the linearized two-port form of any non-linear two-port device, if you linearize them and take only for very small signals, you can linearize them and then take only the first order Taylor series terms, you will get a circuit like this. Okay, so now the question is whether all circuits like this will act as a good amplifier or not. Okay, that is what we were trying to answer in the last lecture. So now let me put it in words, like in order to get maximum gain, okay, out of a two-port network like this, okay, linearized two-port network, what should we do? Okay, the constraints, the first one, okay, you can say that the first one is that the y12 here, this particular term, should be 0. Okay, the reason is that, see, y12 is nothing but the effect of output onto input. Okay, so y12, what is y12? Y12 is the effect of v2 which is added to i1. I1 is the input side, right? And whatever I1 change, if I1 changes according to V2, that is what this Y12 does, right? If there is a change in I1, because of V2 or V23, then that would affect my, V13 also, which I really don't want, right? The point is that I don't want any change at my output to affect my input. The best example would be to say that, if you talk through a mic, and then you get, that is your input. Whatever you are talking through the mic is your input or the signal, and whatever you are getting at the output at the loudspeaker is your output, right? Now, if suppose you do something to the loudspeaker, say for example you disturb the volume of the loudspeaker, okay, you increase the volume, or you do something at the loudspeaker, you keep some other say a mobile phone near to the loudspeaker, and then you hear unwanted sounds, or for example if you tweak the volume of the loudspeaker, more often you would see a cranking sound on the mic, okay, or that effect, even without giving any input to the mic, you get some kind of output to the output at the loudspeaker. That is something you don't want, okay. So I repeat, basically you disturb the output, meaning you change some of the parameters of the output, or you increase the volume of the loudspeaker, to be a practical example. You should not affect the input. That is the logic, right? Even if I don't, if suppose say I don't talk anything at the input or anything at the mic, okay, I should not get any output at the loudspeaker, even though I increase the volume or do something. But then more often, if the y12 is not modeled properly, if that is not 0, you disturb the output, meaning you increase the volume at the loudspeaker. Even without giving any input, you get some kind of a disturbance noise, okay, which is something you don't want, okay. So if you want, and another reason is that if you try, see, indirectly it is like saying you try to solve this circuit, okay, or meaning you try to get v out versus v in of from the circuit. You will realize that having y12, okay, would make y12 would appear at the denominator, and then there can be some combinations for which the gain will go to infinity, okay. That is indirectly saying my changes at the output will affect my input, okay. So which is something that I don't want. So in that case, what would I do? I would make my y12 0, or I would choose my device in such a way that it has its y12 very close to 0, okay, or even 0. In that case, I can completely avoid any kind of instability that will happen, okay. So y12 first should be 0 for unconditional stability. So if y12 goes to 0, so what is the next thing that you want to do? Okay, so you see, if y12 goes to 0, the circuit will change something like this. This particular component is not there anymore, okay. This is the meaning of y12 going to 0. So when a current y12 goes to 0, this current essentially goes to 0. That means this is open, it's not short, this will be open. So across these two terminals there won't be any current. That is what it is, okay. So all the I1 will flow through y11 only, okay. That is the idea. Now what do you do? So let me redraw the circuit, okay. Let me redraw the circuit. So I will have a situation like all of my y11, all of my I1 would flow through y11, okay. Now this is the port 1, input port rather, okay. I am not now bothered about the output. I know output will stay intact just like this, okay, but I am not really bothered about it now. So let me do the analysis only at the input. So what I would do, what I would actually add additionally, at the input of the two port, I would give my input, right. I would give my input voice signal or some kind of speech signal, whatever, okay, which is mostly which can be represented, whatever input I am going to give at the first port, which is the input port, can always be represented by its own Thevenin equivalent or the Norton equivalent, right. So I am going to represent in terms of its own Thevenin equivalent. So any source can be represented by its Thevenin equivalent, which is some Vs and some Rs, okay, V Thevenin and R Thevenin, okay. This is this particular thing is the signal, okay, some kind of signal that I am giving as the input. This could be my speech signal, whatever is coming, whatever I speak into the mic can be modeled using this voltage and a resistor, Thevenin equivalent of it, right. So this could be my speech signal. And remember, this V13 is across this 1 and 3. This is 1, this is 3, so this is V13, okay. Now what happens? I want to have maximum gain out of the amplifier, right? So what do I mean by gain? So whatever I speak into the mic should be amplified. Okay, so for that, first of all, whatever I speak into the mic should properly go into the circuit. Okay, meaning there should not be any kind of attenuation in the amplitude of the signal that I feed it as the input, right? That is what I mean by saying what I feed in first of all should go without any loss. Okay, but what happens if I feed a Vs here like this, and the source, no source is ideal, so that's why they will always have some kind of source resistance. Okay, and if there is another resistance here, the voltage that I give as the input will be divided between these two resistances, right? So if this resistance is going to be finite, okay, there will be always some kind of a voltage division. Okay, so what I want all the voltage here to appear across this V13, then only this V13 will come here and affect my output side. Okay, because all the V13 I want, the V13 is something that is affecting my output current. I want all of my Vs to appear as V13, right? And that is possible only when this particular resistance is infinite. So Y11 is the conductance. So if I want the resistance to be infinity, the Y11 conductance should go to 0, right? Then only you will have all the voltage that you give as the input appearing across V13. Okay, so the second condition is to make Y1 to 0. Okay, and the reason is that Y11 0, or you can say R11 or input impedance Ri, you can say that is equal to infinity. In other words, conductance is 0. Okay, this is to have no voltage division. Okay, at the input port. Okay, so let's go for the third condition. So the third condition is that I want my Y21. So I'm talking about Y11, Y12. Now I go to the next slide, where I have Y21, and the Y21 I want it to be very, very large, as large as possible. Meaning tending to infinity. That is also okay. Okay, so that is what ideally I want. Why I want like that? Because you see, Y21 if you see, that is the effect of input port on the output current, right? Y21 is nothing but the effect of input it will, this will configure my effect of input voltage on the output current, right? So that is what here you see, that if suppose I have some voltage at the input, that will be multiplied by this Y21 to give output current or some part of the output current, right? And if this is very, very large, okay, then my output current is going to be very large for some input that I am going to give as V13. So I want Y21 to be very large, so that my I2 will be very large for some V13. And why I want I2 to be very large? Because if I connect some load here, and I2 is something that is going to be flowing, going to flow through that load. Okay, and current multiplied by that load resistance is going to be my output voltage. So if I want my output voltage to be very large, I want my Y21 to be very, very large. So that is why we have chosen Y21 to be very large. So the fourth condition should be obviously on Y22. Okay, so what do we want the Y22 to be? So let's draw this circuit again, just to clarify what should be Y22. Okay, so this is only at the output side. I have drawn at the input separately. So now we know that Y21 to be very large, and then I have Y22 here. Okay, so here let me say this Y11 should be 0. Okay, so this is open, so this is also gone. Let me do it, and this is tending to infinity. Okay, so here this particular current is I2. Okay, and this voltage here is V23, and here is where I am going to connect the load. Okay, which is external to my two-port network. Okay, so what happens? What will be my output voltage? First of all, my output voltage is the voltage across this RL. Voltage across RL is V naught, output voltage, right? And voltage across RL, okay, I want this voltage to be very high, right? So I2 is the maximum current that I can get out of my two port network, okay, and this will be maximized when Y21 is maximized, right? For whatever value of Y1, V13, I could actually connect them like this. This is port 3, this is port 2, okay. For whatever value of V1, if I have Y11 equal to 0, V13 will appear directly here, okay, and if I maximize Y21, then I am going to get maximum I2, okay. But you see, this is basically is the current that is going to flow through these two resistors, okay. But what I want, this is the maximum current, because this is something maximize Y21 times V13 is the current, and I want all of this current to flow through RL, okay, then only I can have maximum voltage. But if I have Y22, I have, it will actually, do a current division, and some of the current will flow through Y2 also, which I don't want, okay, because I want all the current to flow to RL, because this is where my output voltage will be, it is what it will be contributing to my output voltage, okay. So I want to eliminate this Y22 so that I will have all the current flowing through RL, okay. Otherwise, if Y22 is active, then there will be current division. Part of the current will flow through Y22 and part of the current will flow through RL, okay. So to have maximum gain or maximum output voltage, I want this Y22 to go to 0, meaning this is also open, because Y22 is a conductance. Conductance going to 0 means resistance going to infinity. So this one will be open, okay. So Y22 also I want to go to 0, or output impedance R out, okay, RO or R22 also you can say, should go to infinity, okay. This is to have no current division at the output side, okay. So if you do all this, okay, if you satisfy all this condition, this is basically to have maximized gain, then your two port network will look something like this. This is 3, this is 1, and this is V13, and I1 is equal to 0, right? Because no current will flow through, because you said Y11 also 0, Y12 also 0, so nothing will be there on the input side. On the output side, you have Y21 V13, where Y21 is large and this is V23, okay, and Y22 is 0. If you have the incremental equivalent like this for any device, then I am claiming that I could use that device to build amplifiers. That is what I am claiming, okay. If you have any two port device whose incremental equivalent would look like this, then I can use that device as an amplifier, okay. So this is what I am claiming. But then it is more meaningful to look at the large signal behavior of any device whose incremental equivalent would look like this, because in reality, whenever they manufacture devices, they will do IV characterization or IV measurement, or terminal characteristics measurement. They will essentially plot the current versus voltage of a two port network or a two port device, okay. So if a device's two port incremental equivalent should look like this, okay, which is what I am claiming for it to be an amplifier, then how its IV characteristics or DC IV characteristics should look like, okay. Like we saw for a diode, the characteristics will look like this, right? That's a two terminal device. That is what I mean by DC IV or IV characterization or terminal behavior, okay. So for a two terminal, it was looking like this for a diode, but then now it is a two port or a three terminal. How should it look if the incremental equivalent is like this, is something that we'll see now, okay. So you see, let me draw the incremental equivalent again. Incremental picture of an amplifier. amplifying device. Okay, it's a 2-port device that we are talking about. Okay, so it looks something like this. This is port 1, port 3, and I1 is equal to 0. Okay, this small I basically means incremental quantities. Okay, and this V13 is also incremental quantity. Okay, and here every single quantity I draw in the incremental picture is an incremental quantity that is entirely different from the DC value. Okay, these are all small signal values, the delta V values and delta I values. Okay, that is what I am representing as small letters. I am just skipping delta. Okay, just for the sake of decluttering. This is Y21 V1, this is V23. Okay, so essentially my Y11 is equal to 0, Y12 is equal to 0, Y21 tending to infinity or very large, Y22 equal to 0, right? And my equation is something like this. I1, this is, I'm sorry, I1 is equal to Y11 V13 plus Y12 V23. Okay, and I2 is equal to Y21 V13 plus Y22 V23, in which I am saying these are the constraints. Okay, so obviously Y11 Y12 0 basically mean these two terms are 0, so I1 is equal to 0. Okay, and this is very large and Y12 0, so you have only this expression in the small signal equivalent. I2 is equal to Y21 V13. Okay, so expression wise whatever we have derived is being consistent. Okay, now what should be my large signal? So this is small signal quantities. I1 I2 V1 V2 V13 V23 are small signal quantities. Now in large signal domain, I know this Y parameters are derivatives of my large signal quantities. For example, Y11 is equal to dou I1 by dou V13. Okay, at some operating point. That is what we said. If you remember the Taylor series expansion, this is what we denoted as Y11. Okay, similarly Y12 is equal to dou I1 by dou V23. I would have written V2 or V1 only there. I would have skipped 3, assuming that 3 is grounded. Now I am trying a generalized case where 3 need not be grounded or 3 need not be 0. Okay, at the operating point. By operating point, what I mean is the point at which you operate the device, some DC voltages and currents. Okay, that is what we mean by operating point. Okay, or the quiescent points, whatever we discussed for the diode, the same thing. Okay, now Y21 is equal to dou I2 dou V13. Okay, at the operating point, and finally Y22 is equal to dou I2 by dou V23 at the operating point. Right, now it's very clear, and I know that this parameter should be 0, this parameter should be 0, this parameter should tend to infinity, this should be 0. Okay, so let me draw the characteristics. Okay, because I know what their slope should be at some operating point. I may not be able to draw the whole characteristics across all the voltages, but then I would be able to do at that operating point I am talking about, where I want my device to act as an amplifier, because I know their slopes, right? So let me first draw I1 versus V13. Okay, where V23 will be a parameter. Okay, and this is how you draw the two-port input output characteristics, right? You take one voltage versus one current, and then you take the other voltage as a parameter. Okay, an independent quantity versus a dependent quantity, and other dependent quantity will be a parameter, right? I'm sorry, these are independents, right? These two are independent and this is dependent. I is dependent on voltages. Okay, so you plot independent versus dependent versus independent, and other independent will be a parameter. Okay, so similarly you will have another plot with I1 and V23, another plot with I2 and V13, and the last plot with I2 and V23. Okay, so the slope of this I1 versus V13, okay, this is Y11, which should be 0 at some operating point. Okay, I don't know whether the slope is 0 all over, but at some operating point that I am interested in for it to be act as an amplifier, so there it is going to be 0. So if the slope is 0, I would have something like this, and this is the operating point I am talking about. Okay, so slope is 0. So this is how the characteristics will look like. So what about here? Here also the same thing. Okay, so I1 versus V23, so the slope of this curve should go to 0 at that operating point. So I am putting it to 0 at some operating point. This, when I draw a straight line, the slope is 0. I am not bothered about their absolute values. I am just bothered about the slope of this. Okay, at around this operating point, this is the operating point. Yeah, this is the operating point. So now tell me, so here V13 is a parameter, here V23 is another parameter, meaning if I change V23, the curve may or may not change. Okay, that is what we have to see, and that depends on this curve, right? For example, if I change V23, okay, and around the operating point, if I change V23, my I1 is not changing, it is remaining constant. That is what this graph says. So here also for I1 versus V13, if I change V23, I1 is not changing, right? Here if I change V23, I1 will not change. So here also you change V23, I1 is not going to change, so it will be on the same line. Here also if I change V13 here, I1 is not changing. So if I change V13 as a parameter in this graph, here also I1 will not shift. Okay, it will stay on the same line. Okay, so here I want the slope to be very large. So ideally if I put a straight line, that is infinity. So infinity, I want it to tend to infinity, but infinity is not really possible. So let me draw around the operating point very large slope like this. Okay, so this is the operating point here, and this slope is again 0. So I will have a situation like this around the operating point. Okay, now here V23 is a parameter, here V13 is a parameter. If I change V23, okay, if I change V23, I2 doesn't change at all. So if I change another value of V23 as a parameter in this plot, I2 will not change, right? So it will stay on the same line. Okay, so another V23 also, it doesn't matter, it's not going to change. But here what happens, if I change V13 by a small amount, I1, say for example, if I change V13 from here to here, okay, from here to here, I change V13. So my I1 changes by a very large amount from here to here. So if I choose another value of V13, my I1 will change by a very large amount. I2 will change by a very large amount, sorry, not I1, because the slope is very high here. So again another operating point, I will have a different situation like this. Okay, this is for variation V13. So if if this two-port device is going to be passive, and which will be true because all the devices are passive, they cannot generate power. Passive means, as I said, they cannot generate power. Their V into I will be greater than or equal to 0, or their characteristics should lie only in first and third quadrants, right? So if all these devices are going to be passive, then what will happen? If I keep on reducing the voltage and go to negative voltage, they should cross the origin, so they should go like this, right? And they should cross the origin here also, so they should go like this, they should go like this. Okay, they should cross the origin, right? And here also they should cross the origin, and here also they should cross the origin, right, if it is going to be passive. So if I can encounter a device, okay, which has a characteristics very similar to what I have drawn here, large signal input output characteristics, okay, or large signal terminal characteristic, then I can use that particular device as an amplifier. Okay, it need not follow this trend also. It could actually do something like this and then go to 0. That is also okay. And say for example this is also okay, and this also okay, something like this also okay. It doesn't matter. But what I'm trying to say is, around the operating point that we are interested in, okay, it should have the slope 0 for I2 V2 and then large for I2 V1 and so on and so forth, like whatever we have discussed. So we are interested in the characteristics only around a particular operating point, at which if these conditions are satisfied, then it will act as an amplifier. Okay, and there are some devices, okay, which satisfies these characteristics, and which we will be looking at in the rest of the course, okay, which that can be used as amplifying devices. So one such device is the MOSFET, okay, which is a very useful device, and it's more commonly used for audio amplifying applications and things like that. The entire industry nowadays is CMOS industry or MOSFET industry. All the IC design is involving MOSFETs, okay. And another device is the BJT, which was actually in practice before MOSFET dominated the IC industry, okay. And it's useful to learn both the devices, but then most of our discussion will involve MOSFET, and you can always directly extrapolate the results that we obtain from the MOSFET to BJT. So I'll touch upon the BJT also, okay.